All right, so you're looking here at a distributor. This is kind of like one of the staples of the automotive world that has pretty much disappeared from the norm, but are still going on 30-year-old vehicles and stuff. This was GM's electronic ignition, right? So one thing that you have to recognize is that none of this stuff was made in the middle of nowhere, right? Everything was built upon. It started with something. First thing we had, the very first thing, we had a distributor of some kind, and we had a set of mechanical contacts. There would be like an egg-shaped thing around the rotor, and as that would turn, it would spread the contacts apart, and they'd come back together, and there would be our breaking of our ground circuit. Those things wore off because every time they came together, there was a spark happen because it was current flowing again. So they would last, you know, 15, 20,000 miles and wear out. And then it would have to be replaced. So then this kind of thing came, electronic ignition. Electronic ignition allowed you to get this same control and not have a part that needed to be replaced. But we had that same spark happening between the distributor rotor and the distributor cap, so naturally they wore out over time. So we still had stuff that needed to be replaced, maybe every 25, 30, 35,000 miles, something like that. Now, over the time, we've always dealt with fitting stuff in cars. So what General Motors came out with is they figured out how to incorporate everything into one thing. So the coil, which is an E-coil, lived inside the distributor cap with a cover. We had our rotor. We had our plugs that would plug into it. So our primary signals would come through our pickup coil, signal to the ignition module, which lived inside this as well. And everything would be contained in one thing. This was considered HEI ignition, and this was the standard on all GM stuff. The large diameter cap gave us space between the spark plugs to help prevent one spark from jumping to a different cylinder. This was a very reliable system. Everybody who had points in their cars, which was that mechanical point setup, just swapped in this distributor. They had to replace the power supply to it, and boom, they had electronic ignition just like that. It's amazing. It's a thing of the past now. Ford used a thick film ignition module. Okay, this was attached to the distributor, and it used an epoxy E-coil, which is similar to the one that we showed in the beginning. The TFI means the electronics are made in layers and then smothered and sealed up with a thick film. This type of system had its own share, and there was a period of time where they all went bad. Heat is what took them out. And here's what those looked like. This is what they went to when distributorless ignition came into the equation and the distributor rotors went away. Remember I talked about heat? Look at the heat sinks they built onto this. Now this is a fun one here. This is waste spark. This is what our 3800s that we love so much in our Buicks and our Impalas and our Monte Carlos. This is a waste spark system. So it fires one cylinder while the piston is on the compression stroke and into a paired or companion cylinder while that one's on the exhaust stroke. In a typical engine, it only requires about 2 to 3 kilovolts to fire a cylinder on the exhaust stroke, and the remaining coil energy is available to fire the spark plug on the compression stroke, and that's about 8 to 12 kilovolts. This means both spark plugs fire at the same time. When one, let's say cylinder 6, is on the compression stroke, the other cylinder, let's say 3, is on the exhaust stroke. The spark that occurs on the exhaust stroke is called the waste spark because it does nothing useful. It's only used as a ground path for the secondary windings of the ignition coil. This system requires a crank sensor. Now, if you look over here, notice you have your ignition module. Notice your power transistor in here and your chip that's in there and your battery power going to it. There's your divorced coil. Notice one set of windings is here for your primary. The other one's on this side for the secondary. Those two lines indicate they are not connected to each other. So what happens is your spark jumps out of your coil. Now notice this coil has 2 secondary ports on it. The spark comes out, goes down, jumps in the spark plug, jumps from the spark plug to the grounding hook, flows through the metal of the engine block, called common iron, to its friend, jumps from the grounding hook back to the electrode, up the spark plug wire, and back into the coil. How about that to twist your mind? Now, these are on a lot of vehicles. These were used on Hyundais, on Toyotas, on Hondas. Anything that uses one coil for 2 cylinders. Hemi, Dodge pickup trucks. Right? Anyone that has 2 secondary signals to 1 coil. Right? Coil on plug is our most common thing that we all have now. It's known as coil on plug. If it's on an LS motor, it's coil near plug, or it's known as coil over plug. 1 ignition coil is used for each spark. It's only got 1 port, therefore it has married windings inside them. This system eliminates the spark plug wires, which were often causes of electromagnetic interference, and another maintenance item that needed to be removed. Right? No more spark plug wires. So this sits directly above, and most of your cars probably have this type of system on it. All cars control the timing of the spark. The ignition timing can be retarded, which means backed up, or advanced, which means drawing it forward, on a cylinder by cylinder basis for maximum performance and to respond to spark knock, right, to knock sensor signals. Over here, you're going to see the different ways that we kind of work with this. So timing is the moment that the spark occurs in the combustion chamber based on the power stroke. Advancing the timing at different RPM can yield more power. Centrifugal timing advance is the faster it spins, these counterweights swing outward, and when they swing outward, they move the plate that's responsible for the rotor position, and we can advance timing that way. Versus a vacuum advance, right? If you look over here, we had a vacuum line connected to a diaphragm, and as vacuum applied, that diaphragm would pull that same plate. So the vacuum advance would pull the plate, advancing the timing, and the centrifugal weights would advance that even further. We generally run high 30s, 30 degrees of advance, 32, 36. If we advance too far, we end up on the next cylinder that's to be fired. The computer generally controls the timing advance in most of our vehicles nowadays, and electronic spark timing is an example of that. We have the ability to retard the timing. So our knock sensor picks up that spark knock, that detonation, that pre-ignition, and it's able to automatically reverse that and lower the spark advance to make that problem go away. Base timing is a lot of times a connector that's somewhere in the wiring harness that when we remove it, we take the computer out of the equation and we put it to the actual base unadvanced timing that the car can run on. When we look at our tune-up specs, on older cars, we'll find a timing specification. What should our base timing be? On the same token, if we run full advance, we should see the timing advance to that level once we get beyond that. And I think I'm going to include a video for you on a timing light so you can see what a timing light looks like to be able to use it. I kind of make something like that happen in the classroom where I white out the crankshaft pulley. But I'm going to find a video and I'm going to put it onto your lessons also. The biggest thing is you should look up the description operation of any system you're working on, and you'll learn all the players and how it works. Now, take a look over here. This is why we need timing advance. So when our engine's turning, we need 3 milliseconds to keep that spark plug engaged to burn up our mixture. So when our engine's at low RPM, we got 3 milliseconds. The piston goes by, 3 milliseconds it goes. As the RPM increases, that piston's going to go past faster. In order to get 3 milliseconds, we need to fire it sooner so we can have our same 3 milliseconds before we get to the next cylinder. And that's our reason for it. So naturally, all the speeds in between have a different degree of advance, and that is timed into a floating timing advance. So sometimes it's at 41, sometimes it's at 20, sometimes it's at 8, right? All depending on the speed